We compare the graph of the function y equals f of x with the graph of y equals a f of x to see why we call this a vertical stretch of this. Now we've already seen this behavior with the squaring function, with the y equals x squared function. We've seen why multiplying x squared by a number vertically stretches the graph. This happens for any function, and the way we explain it is going to be very similar to the way we explained it with the y equals x squared function. If this is any old function f of x, then at any point x, the value of f of x is given by the length of the arrow from the x-axis up to the graph. If we want to find a point of the graph af of x corresponding to x, then we have to multiply the length of this arrow by a to get the length of the the value of the af of x function. For example, here a is about 2, so we have to just about double the f of x arrow to get the af of x arrow from the x-axis up to the af of x graph. We do this for every point. If x is over here, this arrow represents f of x. We about double the arrow, we get af of x, again assuming a is still 2. If we do this at every point, it should be clear that our graph is going to double the distance from the x-axis of the f of x graph, so that every point here will be twice as far from the f of x from the x-axis as the f of x graph is. We call this process vertically stretching the graph by factor a. The graph will end up a times as far from the x-axis as f of x. Got a couple of cross-outs here, that's a little sloppy, but we'll live with it for now. We got y equals f of x plus c. Okay, what does this do to the f of x graph? Well, it simply adds the value c to the existing y value. So if we have the f of x graph here, every point will be raised c units. Every point raises by the same distance. And we get the graph of f of x plus c. This is called a vertical shift, c, by c units. Okay? Now we also have horizontal shifts, and we can understand a horizontal shift for function y equals f of x. Let's look at y equals f of x minus h as opposed to y equals f of x. We'll start by looking at a table. Okay, let's assume that f of x is defined in this region from -1 up to h plus 1, whatever h plus 1 is. And note that when x is 0, what does y equal? If y equals f of x, then y equals f of 0, right? And when x is -1, y equals f of -1. When x is 1, y equals f of 1. Now we ask, when does y equals f of x minus h take the same values? When will we get, for this function, when will we get f of 0? Well, we're going to get f of 0 whenever x equals h, because then we'll have h minus h, which is, of course, 0. So when x equals h, the y equals f of x minus h function is f of 0. If x is h minus 1, then h minus 1 minus h is -1. We have f of -1, and h plus 1 similarly gives us value y equals f of 1. So we see that the same three values occur here as here. Particularly the f of 0 value shifts from here to here, from x equals 0 to x equals h. These other values shift by distance h on this graph for this function. And if we look at the graph, assuming that h is here and 0 is here, okay, if this is a value f of 0, if f of 1 is represented by this point in the y-axis and f of -1 by this altitude on the y-axis, then the graph of f of x will go through these 3 points and might look something like this. On the graph of f of x minus h, when x equals h, as we saw, y equals f of x, so that the f of 0 value shifts from here to here. The f of 1 value similarly shifts from here to here, and f of -1 from here to here. So we have these 3 points, which are in the same relationship to one another as these 3, and we assume that the graph here or we see that the graph here is going to have the same shape as the graph here. Just shifted h units to the right.